Video game logic isn't always binary. Sometimes you need to adjust according to a scale rather than a switch. Think of walking in Skyrim because you are carrying too much to be able to run, only to start running after dropping one bucket. Compare that to improving your chances at getting a better drop in Mario Kart depending on how far behind you are. Today, we'll learn how to make a scale logic using the dot product, and apply this by creating a responsive jet boots ability. Let's dive in. Okay, so let's break it down. Here is our player. We want our jet boots to apply force in the negative direction to where we aim, like so. What we also want is for our force to slowly decrease, otherwise our player will fly off the screen very quickly. But what about if we want to change direction, or if we're falling and want to get up quickly? Well, in this case, we'll require our boots to give us a stronger push rather than a weaker one. So now, after we designed our logic, we can summarize it in this diagram. We want to apply a force in some direction. If the player is already moving in that direction, then reduce the force according to how fast it's going. If the player is going in the opposite direction, then increase the force, so that it can course correct. Now that we've expressed this logic, we need to translate what we understand in words into something that our code can understand. This is where the dot product comes in. Here is the key thing. The ratio between the dot product of two vectors and their multiplied magnitudes tells us how aligned they are. In reality, the result is actually the cosine of the angle between the two vectors, but we will look at its physical interpretation, because that's more intuitive. The more aligned the vectors are, the closer the ratio will be to 1. If they're opposite, the ratio will be closer to -1, and if they're perpendicular, then the ratio will be close to 0. If you remember, in the first video about vectors, we learned how to divide a vector into x and y components. Now we're doing something similar, just rotated. Instead of projecting A onto x and y directions, we're projecting it in the direction of B and perpendicular to it. The dot product between A and B gives us the magnitude of the B component of the A vector. For the purposes of understanding it, you don't really need to know how to calculate a dot product, and Unity actually has a method for that, so you don't have to do it yourself. But for completeness, and so you can recognize it when you inevitably run into it in the future, the calculation process is simply multiplying the respective components of each vector and summing the results as shown on the screen. As you can see, the result is not a vector, but a simple number, which is called a scalar. This is why the dot product is also referred to as a scalar product. Now that we have our value that tells us how much our velocity is aligned with the force vector, let's take a look at how to implement this in code. Our two vectors are the force direction and the velocity. To get a sense of how fast we're going in the direction of the force, we first normalize the force direction, because only its direction is relevant to this calculation. Then we take the dot product between it and the velocity vector. That gives us a number representing how aligned our movement is with the intended boost. Now we have two options on our hands. The first is to set a maximum speed and tell Unity that if this value exceeds it, then stop applying the force. We can do this easily by using an if statement. That may be a simple solution, but it feels clunky and unrealistic, which is not what we aim for. The second option is to scale our force with a little more math. So we'll basically create an updated force variable that will be the original force times a scaling factor. Here's how an engineer would think this through. We have a force, a maximal velocity, and an expression of how close the movement is to that velocity. We want our scaling factor to be 1 when you're standing still, 0 when you're moving at the maximum speed in the right direction, and higher than 1 when you're moving in the wrong way. So, the simplest way of doing this is tracing a straight line between these points, and that becomes our formula. Here, A is the aiming direction, and V is the player's velocity. Notice that we divide by the maximum velocity. This is because the aiming direction's magnitude is 1, so there's no point in dividing by it. And also, we want this ratio to be 1 only when the player reaches the maximum speed. So we divide by that speed and not by the current player's speed. We're just using a basic line equation from middle school. Y is our scaling factor, and x is the dot product divided by the maximum velocity. We want y to equal 1 when x is equal 0, and y to equal 0 when x is equal 1. That gives us the slope of -1. So the full equation is just y equals 1 minus x. Now let's take all that and apply it in our code. Now see what happens. If the dot product is close to 1, the movement's already in the right direction, right? So the force will be close to 0, as you can see from our equation. If it's negative though, the scaling factor will be even larger than 1, which will increase the force to get you right back on track. Isn't that super cool? With just a single line of math, we've built a flexible, reactive system. Jet boots that correspond to your movement according to a preset logic. That's the power of vector maths. Once we're happy with our logic, we call this function in the fixed update method. Make sure you don't call it in the regular update method, but in the fixed one. If you'd like a full tutorial about how to create this jet boots mechanic, please let me know in the comments. With some balancing and some more polish, we have our functioning jet boot system. Thanks for everyone who watched this far. I hope you liked this video and learned a lot from it. If you did, as usual, please consider giving it a like, a comment, or share it with one of your friends. And if you like these types of videos in general, subscribe and join our growing lab. In the next video, we'll take the things that we learned in this series and apply them in a fun tutorial where we'll build a turret for our video games, and you're all invited. See you there. Cheers, guys.